start. My name is David, and today I will tell you everything you need to know about Project Loom. I will give you some examples and tell you all about the pitfalls, and I'll give it to you in the form of an introduction. I'm David. I am a software developer in the Netherlands for Team Rockstars IT. I have been doing this for around 7 years now. And you can follow me on Twitter or, well, some other ways. You can find them on my website. So let's start, because we have a lot to cover today. I will start with the current situation. How are we using concurrency now inside Java? Then I will slowly go into virtual threads. What are they? How can you use them? How can we create 1 million of them, or even 100,000? And then we will slowly go into structured concurrency, where I will show you how you can manage all these threads. And at the end, there is some time for a Q&A. So questions, you can ask them using Slido. I have the URL and the code in the room on the screen. So if you have any questions during the presentation, just ask them. And then at the end, I will go over them. And if you don't have questions, you can still vote on other questions, and then I know which one I have to answer first. But before we start, a word of caution. Virtual threads and structured concurrency aren't mainstream yet. They are meant to be going mainstream with Java 21, which will be released in September. So until that time, there may still changes be made behind the scenes, especially for structured concurrency, because it's in an earlier stage than the virtual threads, because they are almost done. So please keep that in mind when you are going to try this out at home or after this presentation, when you want to try out virtual threads. So let's start with the current situation, and that are just the threads that we are already familiar with. Can I get a hand up for everybody who has done something like this before? That is almost everybody. That's really nice. So what we do here is that we just create a normal thread inside Java. So we use the constructor of the thread class, and we ask Java, can you create a thread for us? And when we do that, Java asks the operating system, can you make a thread resource for me that I can use? And then the operating system will, yeah, I will do that for you, and I will reserve some memory for this thread, so along the size of a few megabytes. And then we have a thread inside the operating system, and then we can use that inside Java. So a thread in Java is just a very thin wrapper around a thread that is managed by the OS. And that is also why I put the platform there before the thread in the title, is because during this presentation and, well, during your coding later, you're going to talk about threads, and then other people have to know what kind of threads is he talking about. Is he talking about the threads that we already know, or the new virtual threads? And to tell them apart, the old threads, or not really old, but the threads that we already have, they are now called platform threads. And they are called that because they are managed and scheduled by the operating system. And virtual threads are not managed by the OS, but we will go into that a little bit later. So at line 1, we have our thread, and at line 2, we will just start a thread, and it will start running the task that we have given it. And creating a thread for every task that we have is a very convenient way of programming, because then we can just create a thread when we need to and discard it when it's done. While it is very easy for us to work like this, because then we don't have to keep track of threads, we don't have to pull them, it's just very easy, straightforward. But the wasteful thing here is that when we create a thread, we are going to make this very expensive resource. We have to go outside of the GVM. We have to ask the operating system to do something for us. We have to go back. We have to reserve some memory, which are all very expensive operations. So when we program like this, we are just creating a very expensive resource only to dispose of it when the task is done, while we could use the executor services instead. So while this is a very easy way for us to program concurrent software, it doesn't make the best use of our resources. And since Java 5, we are encouraged to use the executor services instead. And with that, we just pull our threads instead of creating a new one every time. And with a pull, we just have a number of threads that we can reuse. So here on the right side, I have a box of 3 threads. and then I will submit my tasks to this thread pool, and when a thread is available, it will pick up this task, it will run it, and then when the task is done, the thread will be put back inside the pool. And the great thing about this is that we are not discarding our threads, but just reusing them. So we are not allocating a lot of memory each time and discarding it only a few moments later. But the downside of using executor services is, for example, the thread locals. When you have a task that sets a thread local on a thread, and the thread forgets to, or the task forgets to remove this thread local, the thread local will still be available on this thread for other tasks. So when a second task is run on the thread, it can still access the old thread locals. And of course, blocking resources. When we have a thread running outside the pool, just doing its task, but it encounters a blocking method, then at that point in time, we have this very expensive resource, this thread doing nothing, while it could do more useful stuff like picking up a new task to run. But this is something that virtual threads will solve. And then we have async programming, which tries to solve the whole resource problem. But by doing so, it makes programming a little bit harder. And in my opinion, it makes Java code a lot harder to write, even harder to read, and very hard to debug, because you get all these callbacks that you have to manage one by one. And this is where virtual threads come in. The virtual threads are just an alternative implementation of the thread class. So they are not there to replace the threads that we already have, but they are just a new kind of thread. And they are called virtual threads because they are managed and scheduled. The operating system doesn't know anything about them. They live inside the GVM because they are just a concept. They are not bound to a real resource inside the operating system. And the great thing about this is that their stack also lives inside the heap, which gives us the benefit that we can resize the stack as we need. Because when we create a platform thread, we get the standard size stack, or the standard size amount of memory that we can use. And this is along the size of a few megabytes. But with virtual threads, we can just say, okay, I just created my virtual thread. It doesn't need that much memory, so I can just reserve a few megabytes, or sorry, a few bytes, which is a lot less than we would have with the platform threads. And because they are just a concept, we don't have to leave the GVM to create them. So every call is just inside Java, which makes them very cheap to create. They are almost as cheap as creating a string. So they don't have to make expensive calls, and we don't have to allocate a lot of memory, which gives us the possibility to just create a virtual thread for every task that we have. So then we have the best of both worlds. We can create a thread when we want to, but we are not wasting resources when we don't have to. And now that there are enough slides, and I'll switch over to the demo, because watching code is much more fun. So here I have two tasks, the print task, which is not shown on screen. Give me a moment, because it was just working. And then it is there. Okay, cool. So here I have a print task at the top, which just prints hello GeeCON to the console. And I have a sleep task that I will use later, which is just a try catch with a thread sleep of 1 second. So let's try and create a virtual thread. Well, a virtual thread is just a new kind of thread, so I can still use the a normal thread. There's no virtual thread. You will see, and I will call this one VT, short for virtual thread. And I will use the new static method, start virtual thread. We don't use the constructor. There is just a static method that you can use. to start the virtual thread, and then we can just give the task, for example, the print task, and then just a vt.join, because I want to see the result printed in the console. So when I run this, a virtual thread will be created using the start virtual thread, and it will immediately start running. We don't only get the, well, one new method, we also get a builder that we can use, and we can access it using the off-virtual method. As you can see, we also have off-platform, and that will create the old kind of thread that we are already familiar with. So let's use off-virtual, and then I can use set properties, like for example, the name. I will call this the GeeCON VT. And then I can give it either a task using start or unstarted. Well, as the name already does suggest, with start it will immediately start running. And with unstarted, I have to start the virtual thread myself. And also that is just, as we are already familiar with, just using the start method. So when I run this, it will again just print hello GeeCON to the console. So as I've said during the intro, you can also create a lot of virtual threads. So let's try that now, using the new executor services. Because since Java 5, you are encouraged to use the executor services instead of using the thread class directly. And I can do that using the new virtual thread per task executor. Well, as the name does suggest, it creates a new virtual thread for every for every task that I submit. So I can use something like this. Oh, that's wrong. And here I have this new executor. Well, with Java 19, we also get another handy feature, and that is that the executor service now implements the auto-closable interface, which means that I can use a try with resource statement, which means that my threads will be closed, or I will only continue after this try block when all my threads are done. And submitting a task is very easy. You can just use submit, print task. And when I run this example, I don't have to join this thread. But before I can access this try statement, you can see that this thread has to be finished running. So now let's give it a try and create a lot of them. So I will just use a for loop, and let's create 100,000 threads. But let's do so using the sleep task. So in this example, I will create 100,000 threads, and they will all wait 1 second before they continue, and then I can access my try. So let's see how this goes. And as you can see, it just stopped running. And the great thing about this is that we can now have really a lot of threads running at the same time. If I would have done this using the platform threads, I would have run out of memory, because all those threads just take up a few megabytes each, and while virtual threads, almost none. So now let's switch back to the presentation. Let's see how this all works in the background. Because as you may know, my just a laptop, I don't have 100,000 cores in the system. So let's see how this works. So I have here at the top a lot of virtual threads for the amount of cores that I have. So in this example, I have just a 4-core system, and I have created a bunch of virtual threads that I want to run. And these virtual threads run on what is called a carrier thread. And a carrier thread carries out the work of a virtual thread. And the carrier thread is just nothing more than just a platform thread that is there to run the code of a virtual thread. So every carrier thread gets its own kind of queue of virtual threads. They run in a fork join pool using a work stealing scheduler, which means that every carrier thread will work through its own virtual threads, And when a carrier thread is done with its tasks or with its virtual threads, it will just steal a virtual thread from a other carrier thread and it will start running that instead. So when you run virtual threads, you can't be sure that each virtual thread will run on the same carrier thread again. It will be completely, well, not at random, but you can't be sure of it. So how does a carrier thread switch from virtual thread to a new virtual thread? And that's done with mounting and unmounting. So here I have a carrier thread, and it runs a virtual thread at the top, and this carrier thread will start running this virtual thread until it encounters a blocking method. And when this virtual thread is blocked, because it has to do some call to an external system, it has to wait for a database to give some response back, it will be blocked, and the virtual thread in the stack will be copied from the carrier thread back inside the heap, and a new virtual thread will take its place, which means that the stack will be copied into the carrier thread, and the carrier thread will start running this new virtual thread instead, while the old virtual thread is just waiting for some response, but not on the carrier thread. So the great thing about this is that our carrier thread is now always running some work, which makes the best use of the hardware that we have available. But not every method is ready yet. When you encounter a synchronized block or an object.wait, or you make a call to native code using something like GNI, or make use of file system operations, at those points in time, your virtual thread is blocked to its carrier thread, which means that it can't be taken off the carrier thread, but it is still stuck. Well, some great things happen behind the scenes. It will create some new carrier threads that will pick up to help to reduce the load during the blocked carrier thread that was blocked in the first place. But not every method is ready yet, and you may not see the performance improvements that you want when you encounter these methods. And that leads us to the pitfalls. If you use a virtual thread for long-running calculations, like you want to calculate a number of pi, then your virtual thread never encounters a blocking method. And then when it never encounters a blocking method, it won't be taken off the carrier thread, so it will also be stuck. So even though you're not using any of the unsupported methods, you can still have a virtual thread that is stuck to its carrier thread. And with virtual threads, you never want to pull them. They are not meant to be used like that. You just create them when you need to. When you have a task that you want to run, you'll just create a virtual thread then and there, and you can just continue. There are also some use cases where you maybe have used a thread pool as a sort of lock to limit the amount of connections, for example, to a database. So, for example, you don't want more than 4 connections to a database, so you use a thread pool of only 4 threads. Well, as I've said, you don't want to pull virtual threads, so this isn't really an option anymore, and in those use cases, just use a lock instead. And of course, old libraries may not have been adapted yet and could still use these old unsupported methods. So, as I just shown you in the demo, that we have created 100,000 threads. And we can manage them using structured concurrency. And before I dive deep into what structured concurrency is about, I want to start a little bit from the top with something that we probably are all familiar with, and that is structured code. This is just a simple Java method. It's method A, and I make 2 calls, one to method B, one to method C. I combine the results and return it to the caller of method A, which is all very straightforward. So what I have is this very simple flow of my method. I will start at A, call B, call C, and then I will have a result, which is very easy to understand. So when, for example, an exception happens inside B, I can still start my method A, method B throws an exception, and at that point in time, I know I not longer have to continue. I don't have to call method C, and I'm not going to try and create a result because I can't, because I have not getting because I don't get a value from method B. And the same goes, of course, for method C, but then I have already executed my method B, but then I encounter an exception, and at that point in time I also know I don't have to continue anymore to create a result. So the next step is using threads in this example to show you what happens differently. So there is this implicit relationship when using threads. So I again have the same method, but this time method B and method C spawn a new thread to get a result, and I will store them in a future object. And then I will use two get methods to create my result. So again, I will just start method A. I will start up method B. It will start running in its own thread. Then I will start C. It will start running in its own thread. And then I will wait for both threads to finish. So now, again, a exception happens at B, which is really unfortunate. But now I have started method A. And method B spawned a new thread. It's running. It's getting, well, throws a exception. It's stopped. But I have also started a new thread in method C, which is just happily running into the distance. It just keeps going. And at this return statement, only then I find out, oh, my method B has thrown an exception. I can't create my result. So at that point in time, I have to go back, get that thread from method C, and stop it myself, which is just annoying. But the same goes for method C, but it's even a little bit worse, in that I have to start my method B. It starts a new thread. I start method C. It also starts a new thread. But then I get at the return statement, and I have to do the foo.get. And at that point in time, I have to wait till my method B is done running. So I have to wait the entire time my thread is still running. But in the background, I already know I can't continue because method C has thrown an exception. But the method will just wait for method B to be done. So when method B finally returns a value, I get to bar.get. And at that point in time, oh, I didn't have to wait. My method C has thrown an exception, and then I can just stop. So that's just really a waste of time. And the last is that if the parent thread of the caller of method A throws an exception, then I have just two threads loose inside the system that just continue running, but there is nothing to listen to their result, which is just, well, a waste of resources because I then have two threads loose inside my system. So now let's take a look at how structured concurrency solves this by doing a little demo. So what I want you to pay attention to is to what happens inside the try with resource statement. So here I have, oh, you can see it if I do it like that. I have a try with resource statement here at the top that uses a structured task scope. And the structured task scope is used to implement, well, the structured concurrency. And with the structured task scope, we get two built-in shutdown policies. The shutdown on success and the shutdown on failure. And these policies state how your virtual threads are being terminated when something happens with them. So for example, with the shutdown on success, I shut down all the virtual threads that I have when the first one finishes. So here inside the try with resource, you can see I use the new structured task scope of type shutdown on success, which will return a string. And let's just make that a little bit easier with the explicit type. So I have just a structured task scope of the type shutdown on success. So I can use the scope to spawn new virtual threads for my scope, for the scope that I have. And to do that, I use the fork method. And so here I create two virtual threads. One which will get result 1, and the second will get result 2. So when I start running these two virtual, when I fork these, they will immediately start running. But what then? I have this shutdown policy. How do I wait for it? And you can do that using the join. When you see the scope.join, my parent thread will block. It will wait for the shutdown policy to be done. So in case of the shutdown on success, I will wait till the first one finishes. So for example, if result 1 finishes first, the other thread will get terminated, and then I can continue. But how do I know which thread finishes first? I can do that using the result. And the result will give me the result of the first thread that finished. And this is all there is to it to using the shutdown on success policy. But as I've said, there are two shutdown policies. And the other one is the shutdown on failure. And the shutdown on failure policy states that I want to shut down all my threads when one of them throws an exception. So here I have this scope object. It's just a structured task scope of the shutdown failure type. And again, I fork 2 new threads. They will again fetch result 1. The other one will fetch result 2. And they will store it inside a future. And then again, I will wait for those threads to finish using the join. So with the shutdown on failure, I will wait till both threads are finished, or, well, one has thrown an exception and the other one I don't really care about anymore. So to know if both threads are finished successfully or not, I can use the throw if failed. And with the throw if failed, it will just rethrow the exception that the thread has given us. And then the method will just stop there. So when I continue from this, after this line, I know that both of my threads are done. I know that none of them has thrown an exception. So then I can go into the return. And then I have to use the futures. Well, what we are already familiar with is that we will use the get method. But the get method is a blocking method, and we don't really have a use for that at this point in time, because after the join and the throw failed, we know that both of our threads are done at this point, so we can just use the result now, which will just immediately return a result. Looking at the time, I do have time for a third demo, and that is when the 2 built-in shutdown policies aren't enough. So here I have my new a new method, running your own scope, which also has the try of user statement, but I create a new criteria scope. And how does this look? A little bit like this. And just move this to the side. So here I have the criteria scope, which just extends from the structured task scope, and it will turn a product, which is just a very simple thing. It just has a price. It's a very simple object with a price. And I have to only override this single method, the handle on complete, which is called by every virtual thread. So inside this handle on complete, I check if the state of my virtual thread is success. So it has finished successfully. There's no exception has happened. And I check if the price of my product is less than 100, because I'm only interested if the price of my product is less than 100 that I found. If not, just continue creating threads, something, until I found my product that's worth less than 100. And if I found it, just store it in this variable and then just shut down. And that means that it will shut down all the virtual threads inside that scope. So when we go back to the example, it looks really the same like any other structured task scope, in that we create new threads using the fork. So I get a product of 50, 300, and 200. I call the scope.join, and I get the state to show it on in the console, and the last result. So let's run this and see what it prints. As you can see, I have 3 virtual threads started. The one with product 50 state success, because that means the thread finishes. product 3 wasn't successful because, well, it's just 300, it's took too long. Because when we go to that method, which fetches a product of 300, you can see it thread will sleep, so it was just too late. But as you can also see, we have this product of 200, which is a state success. So it means the thread finishes successfully, but we didn't exit the scope just yet because the product was worth 200. It has a price of 200, and we are only interested in 100 or less. So as you can see, when we found this product of price 50, only then we shut down the scope. Let's go back to the example here. So this is what we printed to the console, and when we found our product of 50, we continued from this join and we printed it to the console, which resulted in this line. So that is all there is to it to using structured concurrency. So let me switch back to the presentation. And the pitfall of structured concurrency really is managing the lifetime of threads yourself. Structured concurrency just makes it very easily understood. There are 2 built-in shutdown policies you can use, and it is code that you don't have to maintain yourself, which is also quite a, well, positive. So before I end my presentation, I want to let you know that all you need to get started with virtual threads are just these 2 methods, the start virtual thread and the new virtual thread per task executor. So you don't have to use any of the structured concurrency. You can, but don't let it discourage you. So all you need are these 2 methods to start using it yourself. And that was the end of my presentation. Thank you. And then it's time for the questions. Will virtual threads be visible on the thread dump? I think so, yes. They will be visible, but I have never tried it myself, so I'm not 100% sure. So sorry about that. Can virtual threads replace reactive programming in web apps? I do hope so. But yeah, well, I do hope so, but we will have to see what the future plans out. I say, if somebody say yes, it can. I believe in that. I hope so. Are there thread mechanics to avoid blocking all the blocking all the carrier threads? That's very interesting, but I don't know. From what I read from the Java enhancement proposal, it said that when a carry thread is blocked, it will just spawn new ones. But I thought that was only for selected use cases. So this is very interesting, at least to try. But we'll have to find out. Will it really make it to Java 21? Time is running fast. Well, not as fast as virtual threads, I hope. But the Java enhancement proposal said it was targeted for Java 21, so I guess that means it will be in there, but then again, I see somebody shaking yes, so that is what it means. Targeted for 21 means it will go mainstream with 21. And that were all the questions. Oh. On a multi-core system, will virtual threads be distributed on different cores? Yes, because you will get the amount of carrier threads. So these virtual threads run on a carrier thread, and you will get the same amount of carrier threads as that there are cores available inside your system by default. But of course, with some parameters, you can change that. But by default, you will get just as many virtual threads running at the same time as you have cores available inside your system. You said virtual threads don't work well with system I/O. Isn't the matter of preparing the right? Yes, it is. You just have to use the right APIs, I guess. But from memory, there is also this kernel update for Linux to have the non-blocking I/O. So it would be best to see how that works out with the virtual threads. So yeah, we have to just see how the team handles that. How much performance we get in comparison to platform threads? Well, they aren't like a silver bullet. They won't run faster or compute more than the platform threads do, because they still have to run on a platform thread. The real power of virtual threads is really just in the numbers. You can just create 100,000 of them and it won't be a problem, which really gives you a new way of working, that you can just create it. When you have a task, you can just create a virtual thread and just start running it. So really the power is in the numbers. Do we have a relation between virtual threads and system threads? If we have a system using threads, changing to virtual threads, can we see a difference in memory usage? Well, not really at the start, because you still have these platform threads that are there in the background. So you still need those, but the more threads you'll have, the more memory benefit you can see from using virtual threads, because they don't have that much memory when you create each of them. If there are no virtual thread pools, what is the proper do we have? Okay, do we have a relation? I already answered. Okay, I thought it was me going insane with the questions just jumping. If there are no thread pools, what is the proper way of limiting the amount of active connections when using virtual threads? Just use a lock. Just use a lock to limit the amount of connections. Something like a semaphore, for example. But you should never pull virtual threads. Who was it? The guy behind the Project Loom, he really states that you never ever should pull virtual threads. And if you do so, there's probably something wrong with your design, and you should just restart doing that one. So I believe him, because he knows everything about it. Will there be a way to tweak the number of carrier threads? Yes, there is a parameter that you can, or a argument that you can pass when you start up your application to limit the amount of carrier threads. So yes, you can do it, but I don't know the parameter by heart. So you have to look that up. What happens when we do thread.sleep on a virtual thread? Is there any continuation object stored in the scope? I'm not that familiar with the Kotlin coroutine, so well, what I know is that when a virtual thread is going to sleep, it will be taken off the carrier thread and just put back inside the heap, and when it's waken up again or woken up again, it will just run like nothing has happened. How thread local behaves in virtual threads? That's a very good question. I don't know, I haven't played with it that much, but my colleague Ron Veen is also here at the conference, so you should really talk to him about this, because he is really a fan of thread locals. Could you compare the new Java concurrency model to Kotlin coroutines, pros and cons? What do you think about coroutines? Well, I am not that familiar with the Kotlin coroutines, but I can say that with the virtual threads, it is really just a drop-in replacement, really. Because from the outside, as a developer, you don't see any difference from except the start virtual thread per task, the new virtual thread per task executor. But the end, the executor service and the thread class that you are going to use, well, they don't look any different from the outside. So you should really look into this Kotlin Go routines. How is it better than thread pools offered by frameworks like Spring? I don't fully understand the question. How is it better than the thread pools? I Yeah, Spring is, well, there is some, they are going to use it, but yeah, what is the benefit is that you can just have lots of virtual threads instead of just a few platform threads. As a general rule, could all platform threads be migrated to virtual threads to minimize costs? You can do it, but you won't see that big of a difference because you'll still have the platform threads running. But when you create lots of platform threads already, then yeah, you should really try using virtual threads and see how it works out for you, because they do use less memory. So it's really about experimenting and trying stuff out. It's always fun. So if there are no more questions left, then I want to thank you for being a brilliant audience.